Okay, good morning, everyone. Um, so today, well, in the past couple of lectures, we've been talking about the energy levels of the hydrogen atom. Okay, and those, I'll remind you, are written in the following way. So they depend only on the principal quantum number, which is a positive integer. Okay, and there's a minus sign times e squared over 2a0. And then there's a 1 over n squared. Okay, and so the minus sign is a reminder that we're talking about bound states. The e squared over 2 Bohr radius is also known as 1 Rydberg. And so that's the amount of energy needed to ionize from the ground state to unbound state. So n equals 1 to n equals infinity. And the 1 over n squared factor, that's again the principal quantum number. So one thing we should say is what this does not include. So this does not include small effects that you will learn about if you take Quantum Mechanics 2 next semester. So it does not have small effects. And so we can make a list of what they are. And so I'll put suppression factor here. Okay, and so the different types of small effects are fine structure. And fine structure actually comes in 3 parts. Fine structure has a relativistic part, relativistic kinematic part, and it has a spin-orbit coupling. That's between the different kinds of angular momentum in the atom. And then there's something called the Darwin term, which is another relativistic effect. And all of these have suppression factor alpha squared, which is so roughly 1 over 137 squared. That's compared to a Rydberg, right? So these are very small effects in comparison. There's also, something called the Lamb shift, which is extremely difficult to calculate. We won't actually do that. We'll just quote the answer in the next semester. Those turn out to be suppressed by alpha cubed, but the number in front of them is not so small. So normally you would think if it's alpha cubed compared to alpha squared, then you could just neglect it. But it turns out it's alpha cubed times a fairly large number. So it's not negligible. And then there's something called the hyperfine structure. Okay, and that's basically due to the proton spin in the hydrogen atom. And so that turns out to be also suppressed by alpha squared, but also suppressed by the mass of the electron divided by the mass of the proton, which is a very small number. Okay, so those are all the effects that you have to include to really get the hydrogen atom right. But we can sort of neglect them today. And so if you talk about the transitions between energy levels, which can occur by emitting a photon. So you're in a state n, let's say, and then there's a lower state n prime. These are all given by integers, and so you can transition by emitting a photon, and the photon energy is known because it's the difference between those two states, and so you know its angular frequency. It's 13.6 electron volts over h bar, times minus 1 over n squared is the energy of the state you started with, plus 1 over n prime squared. Okay, and then from that, you can work out the wavelength, which is how the spectroscopers often quote the answers. Okay, and so that's 2 pi speed of light over the angular frequency. And so you can rewrite this by putting in the numbers as 9.11 times 10 to the minus 8 meters times n prime squared over 1 minus n prime squared over n squared. So the way people usually think about this is you fix the final state, and then you ask what happens for various different initial states. So we fix the final n prime state. And then as you vary over all possible n's, that gives you what's called a series of spectral lines. For atomic hydrogen. For any other atom, there's a similar series, but that takes a lot more work to work out. Okay, so this is for different n's transitioning to the fixed n prime. So I think at the last part of the last class meeting, we talked about the case n prime equals 1, which is called the Lyman series. And the Lyman series is all in the ultraviolet, so you can't see it directly. But it's very important in astronomy, the Lyman alpha line. The Lyman alpha line is what you get from n equals 2. So it's the n equals 2 transition to the n equals 1. It's sort of very common in the universe. And so you can do a lot of astronomy with that ultraviolet line. There's the Lyman beta line, which is n equals 3 to n prime equals 1. And you keep going, and then eventually you reach the Lyman alpha limit, or the Lyman limit. The Lyman limit is just what happens when n is very large. When n is very large, you can look from the formula and see that it just doesn't matter very much exactly how large it is, because this is just going to 0. And so you get just a bunch of very closely spaced lines in the ultraviolet. So these are closely spaced. Okay, so the n prime equals 2 case is interesting. That's called the Balmer series. And one of the reasons that's interesting is that's actually in, or at least some of the lines are in the visible. In fact, 4 of them are in the visible. And so you can actually see them with your own eyes in telescopes. For example, the n equals 3 line transitioning to the n prime equals 2 line happens to be red. And you can see this in things like supernova remnants or in star-forming regions that have a lot of atomic hydrogen. So if you look at those regions in a telescope with a true color image, you'll see a lot of red, and that's where it's coming from. The n equals 3 goes to n prime equals 2 line. Okay, and then if you're going from n equals 4, that turns out to be sort of greenish. N equals 5 is bluish. N equals 6 is violet. Okay, and then you run out of luck and they're in the ultraviolet for all the larger ones. So these are in the ultraviolet. Okay, unfortunately, that's it for visible, because if you go to n prime equals 3, that's called the Paschen series. Okay, and so what n's are allowed? Basically any n larger than 3. So you have n equals 4, n equals 5, and then the lines get very close together for n very large, but these are all in the infrared. Okay, and then there are various other series that are named. There's the n prime equals 4 called the bracket, and the n prime equals 5 called the fund.
Sorry, Professor, what section of the book is this?
What section is it? Let's see, let me pull up the text and tell you. So we're on page 147, 148. Okay. And then there's n prime equals 6, which is called Humphreys, and I think they're not named after that, and they're not particularly useful or interesting for anything. Okay, so there's a lot more to atomic spectroscopy, of course, but it's, I think, useful to know at least the simplest example that we can work out, which is the hydrogen atom. All right. So we're about to switch gears a little bit and spend the rest of the semester basically talking about aspects of angular momentum that we haven't covered before, or some aspects of angular momentum that we have covered, but we're going to review them because they're very important. And so we're going to start by talking about spin, which is otherwise known as intrinsic angular momentum, as opposed to orbital. And so one thing that you can do is you can add those two types of angular momentum. So traditionally, when you have a total angular momentum, it's called J. So this is the total. And you can write it as a sum of the orbital part. This is the part that in classical physics would be associated with the actual motion of your particle. And then the spin part, which is just anything that's not associated classically with the motion of the particle. So these are both angular momentum operators. We assume that they commute with each other. And so they're sort of independent, but yet we can add them together to get a total angular momentum. And so one of the things we're going to learn how to do is how to do that addition of angular momentum in a systematic way, which will apply not just to this combination of angular momenta, but any combination of angular momenta. And in fact, not just two angular momenta, but let's say I had a carbon atom, then there are 6 spins and there are 6 orbital angular momenta, and I need to add them all up somehow and understand the commutation relations that would come about from that. Okay, but for now, we're just going to do this pair. And so for the spin, the big difference between spin and orbital angular momentum is, let's say you have an electron, for example. The s squared operator is h bar squared times s plus 1, where s is 1/2. And the important thing about the s equals 1/2 is it's completely fixed. There's nothing you can ever do to change it. You cannot change the spin, the total spin angular momentum of an electron. It's a property of the electron. That's the word intrinsic here. And you can never do anything about it. On the other hand, what you can change is you can change the direction of the spin, and that's given by the z component. Okay, I'll write m sub s to distinguish spin, and that can be 1/2 or -1/2. So that we can change. In comparison, there's also the total orbital angular momentum. Okay, and its z component. Remember, we can't add the x component to this because that wouldn't commute with the z component, so they couldn't form a complete set of commuting observables, but both of these can change. And so by change, I mean you can have a Hamiltonian that changes that if you evolve it in time, will have different values for L. Okay, so if we're going to specify the state of an electron, we want to be able to specify both of those types of angular momenta independently. And so if we have a ket that's going to describe what the electron state is, I can write a expression for it in the following way, that there is a ket that describes it if it happens to have m sub s equals +1/2, and another ket that I'm writing this way, which describes it if its angular momentum spin is m sub s equals -1/2. Okay, so that last label there is the m sub s spin label. We could, of course, just write +1/2 and -1/2. That would be a perfectly sensible thing to do, but we're going to write up arrow and down arrow. Okay, and then this other thing, the first slot of the ket, is just what's specifying the rest of the state information, whatever it is. Okay, and so that could be, for example, it could be the position space wave functions. Okay, but because I have two independent kets here, there are two different wave functions for the electron. There's the spin up one and the spin down one. Okay, and so we have to keep track of both of them. So another way to represent this is with a sort of hybrid notation. This is the completely ket notation, but we can write a hybrid notation where we represent these parts of the kets by two-component vectors, and we leave this part of the ket as a ket. So the way that would work is we can also represent the same state information as a two-component vector of other kets. Okay, and then its bra, or its Hermitian adjoint, would be a row, two-component row vector, each one of which contains a separate ket for the spin up and spin down parts. So just for variety, I've changed notation here. And so I've changed up arrow and down arrow to plus and minus. So that's another common notation. So there's actually three different notations at least that you'll see in different places in the literature or in books. You'll see up arrow and down arrow. You'll see plus and minus, or you'll see +1/2 and -1/2. Okay, in any case, these things are known as spinners, these two-component sets of kets. One nice thing about writing them in this form is that then we have a matrix notation or a matrix representation for spin, which is that S, the operator, is represented by h bar over 2 times the Pauli matrices, which form a vector. So the x component of the Pauli matrix vector is 0, 1, 1, 0. The y component is 0, -i, I, 0. And the z component is 1, 0, 0, minus 1. So we've covered this before, but this is just a review. And so in this language, if we take the inner product of two of these spinors, it will look like the following. So I have one spinor that I'm labeling by 1 and another one that I'm labeling by 2. And then I break it up into its two components. So I have psi 1. I'm going to continue to use plus and minus. For some reason, when I do handwriting, it's easier to do plus and minus. And when I do typesetting, I like up arrow and down arrow. Okay, and so it looks like that. Okay, that's in the original completely ket notation. But then I can switch to the hybrid notation where instead of adding these things together, I take them as two components of a vector. Oops, that was 1 plus. Okay, so there's the two components of a row vector, and then the two components of the column vector for psi 2. And so when I'm taking the dot product of those two vectors, I just take the dot products of the individual parts. So either way, we get the same answer. The inner product has to be a number, and the number it is just psi 1 plus psi 2 plus inner product plus psi 1 minus psi 2 minus inner product. Okay, so that's how inner products of these things work. As a special case, you can talk about the normalization for spinors. And that's just by saying 1 should equal the inner product of a spinor with itself, which from the previous line is now I'm just leaving off the extra label because I don't need it. So this is psi plus, psi plus. I think in the text I wrote it as psi up arrow, plus psi minus, psi minus. Okay, and so unlike the case of a situation where I don't have spin, this time I just have to add the individual parts of my inner product to get 1. So normally I might think I would just have this part, but no, I have to add together the psi minus part. Okay, now, so far we've written the non-spin part still as a ket, but now you can go ahead and turn that into a wave function also. So now we have two component wave functions for the electron. And I'm going to do this in spherical coordinates. Okay, so what we're doing is we're taking the inner product of the position eigenket with the whole two component spinor. And so that is in this two component notation. We just take the inner product of psi plus in the upper entry and psi minus. Oops. This should have been a phi. Psi minus in the lower entry. And so each one of those is separately a wave function. And so there's a psi plus part, which depends on position. I can write r vector or I can write r theta phi. It means the same thing. Okay, and so instead of specifying two kets, one for each of the two spin components, I'm writing just one I'm writing two wave functions for them. And the information in this is the same as in the original complete ket. Okay, and so what have we done here? What representation are we using? This is the R vector, position vector, S squared, S sub Z representation. So any representation is equivalent to specifying a complete set of commuting observables. Okay, and so that's our complete set of commuting observables that tells us what representation we're in. It's basically saying if we know exactly where the particle is at any given moment, and we know its total spin, which is actually fixed and we can't even change it, and we know its z component of spin, then in principle we know everything there is to know about a spin 1/2 particle. You can't add the information about the momentum, for example, because the momentum would fail this C. It doesn't commute with position, and so you can't add it to the complete set of commuting observables. Okay, so now the normalization condition is just this, that 1 has to equal the integral of d3r. But now I have to add together the squares of the wave functions of the two components. Okay, so that's how we normalize spinor representations. Now, suppose we want to work in this representation, but suppose we want to represent the orbital angular momentum operators somehow. So how do we do that? In this representation, we just go back and look at how we did that in the past, and then we do it for each component of the spin. So for example, if you look back at how was the LZ operator, the Z component of orbital angular momentum represented, it was minus I h bar times the derivative with respect to phi. And so what we do is we write a 2x2 matrix with minus I h bar partial phi here, and minus I h bar partial phi here. And then it's diagonal, so we just write zeros there. And so all this is saying is that for each of the spin components independently, L sub z has exactly the same differential operator representation that it had before. And it's diagonal because it doesn't really care about spin. It just does the same thing to all spin components. This is for spin 1/2. If we had spin 3/2, then this would be a 4-component thing. And then this would be a 4x4 matrix, but the LZ operator would just have the same thing repeated everywhere on the diagonal. Okay, and then, for example, L sub x, if you look up somewhere in the notes how that's represented, it's something like I h bar sine phi d by d phi plus cosine phi, I think it's cosine theta over sine theta, d by d phi. But anyway, whatever, assuming that's right, it's just 0, 0, and then the same thing in the lower 4x4 component, right? So everything is just a diagonal operator in 2x2 space, okay? And so I can write etc. for things like L sub y, and the L plus and L minus operators that raise and lower the angular momentum, and L squared, etc. Okay, so that's one nice representation that we can use to simultaneously have orbital angular momentum and spin. But there's a different representation where I don't use differential operators for orbital angular momentum. Quantum mechanics is all about different representations of the same thing. Okay, and so that would use L squared, LZ, and S squared and SZ as our CSCO, or at least as part of a CSCO. I should say part of in parentheses, because we could also include things like the Hamiltonian often, assuming the angular momenta actually commute with the Hamiltonian. So if the Hamiltonian commutes with L and it commutes with S, then we could add that. This is a very common situation. If they commute, then we can add that to the complete set of commuting observables. But right now, we're just going to sort of treat that as a redundancy thing. So what have we done here? We've replaced R, the position operator in our CSCO, by the orbital angular momentum operator. And that has the effect of making these things, the representations of the operators, be just plain matrices rather than differential operators. So in fact, there's an orthobasis associated with this CSCO. And so how would we label the orthobasis? We give the L squared quantum number, the LZ quantum number, the S squared quantum number, which is really, we didn't have to do that because again, it's completely fixed. There's nothing we can do to change it ever. And then the Z component of spin. And then there might be other labels. In fact, there almost always will be other labels. And under favorable circumstances, that would be the energy. Okay, but right now, since we're mostly interested in angular momentum, those are just degeneracy labels for angular momentum. Okay, and so now there's a matrix representation for the spin operators. And the key thing is that they're just diagonal in L squared LZ space. So all that means is that when they're acting on a given member of this orthobasis, it just ignores those two things, and it does what it always does to these labels. And so now you can construct a big matrix representation for this orthobasis. And the same thing in converse for L squared and LZ. They are diagonal in the S squared SZ space. Okay, and so one can write matrix representations for these, although one often just works directly with the Ketsen-Bras. Okay, and so the way that works is, let's say you have LZ acting on one member of this thing. Okay, it doesn't care what S and M sub S and K are. This is just going to give you H bar M sub L times the same thing. That's what it means to be diagonal in the spin space. All right, any questions on that? All right, so as this example shows, one thing we want to do is we want to be able to add angular momenta in general. This is the problem of addition of angular momentum. It has a whole chapter in the book because it's so common. So here's the general statement of what we're trying to do. So recall that a generic angular momentum operator satisfies the following properties. First of all, it's a vector, so it's got three components, each one of which is an operator. And those have to satisfy a very specific commutation relation. I'm letting little j and little k here temporarily be x, y, and z. And so if I take the commutator of any two, it has to be very specifically I h bar sum over L times epsilon jkl times j sub L. Okay, which just means if I take the commutator of jx and jy, for example, then I get IH bar times j sub z. This is the anti-symmetric symbol. Okay, so in fact, anything that satisfies that property, we can say that's an angular momentum. And if it doesn't satisfy that, then it doesn't satisfy, then it's not an angular momentum. Okay, and now we're going to suppose that just like for our spin and orbital case, we have two of these, J1 and J2. Now the subscripts do not mean the components. They just tell you that you're talking about two different angular momentum operators. These commute. So if you have independent angular momentum operators, you always assume they commute. And then you can ask, what is a complete set of commuting observables for this? And one way to make a complete set of commuting observables is to just take each of the complete set of commuting observables for the different angular momenta and combine them. So you could have J1 squared and J1z and J2 squared and J2z. Okay, and then anything else that was sort of independent of both of those. So I'll just write here, and other independent things. Again, a very common candidate for the other independent things would be the Hamiltonian, but not necessarily. Okay, so if you've got a complete set of commuting observables, then we know that you can form an orthobasis that corresponds to them. And so the eigenstates, the common eigenstates for the complete set of commuting observables, we can write in a tensor product form as J1 M sub 1. That's for these two. Tensor product with J2 M2. Or we can just dispense with the fancy tensor product notation and write this as J1 M1 J2 M2. And that's a perfectly good orthobasis for these two angular momenta. And in fact, it's called the product orthobasis. Now, when I say it's perfectly good, that's an exaggeration. It's not perfectly good because it turns out there are lots of problems where you don't want to use that basis. And there's a better basis to use. Okay, and so what is that better basis? So to see what it is, you define J to be J1 plus J2. So what we were talking about previously just had L and S for J1 and J2, and then J was the total. This is going to be our total angular momentum operator. It may not be the grand total angular momentum operator. Maybe we'll have other angular momenta that later we're going to add on to that, but for now it's the total. Okay, and then another choice of complete set of commuting observables would be the following. I still include J1 squared and J2 squared, but now I include J squared and its Z component, J sub Z. Okay, so this is one set of complete set of commuting observables. This is another one. And so its eigenstates, or the common eigenstates of that complete set of commuting observables, can be labeled in the following way. J1, J2, J, and M. And notice there's not really a good way to write this as a tensor product. It's just, that's just the set of states. They're labeled by the eigenvalues of the complete set of commuting observables. So this is another basis called the total angular momentum basis. Okay, and so what is the problem of addition of angular momentum? The problem is to find out how these two different bases can be converted into each other. So we want to find the coefficients in the following. So there's some relation that says if I have a state in the total angular momentum basis, because the other thing is also a basis, this must be a linear combination of the product orthobasis kets. I'm being a little sloppy here because I'm sometimes including commas and not including commas when it's not in my, when I'm not feeling like it. Okay, so that's the big problem that we want to solve here is this always has to be true. Linear combination involves some unknown coefficients. If we know what those coefficients are, then we can convert back and forth between bases as we like. And that's good because a lot of times this is what's going to happen is it's going to turn out to be easy to write down the problem in the product orthobasis, but it's going to be easy to solve the problem in the total angular momentum basis. And so that's why we need to be able to convert back and forth. Occasionally it'll be the reverse, where it's easy to write down the problem in this basis, but easy to solve it in this basis. Okay, so one thing you could ask is there any other CSCO, or could we write down a CSCO that includes aspects of both of these? And so I want to emphasize that's not possible. So let's see, could we have a CSCO that's something like the following? So I specified J1 squared and J2 squared and J1Z and J2Z and J squared and JZ. So I'm going to try to specify everything. And the answer is you can't because, again, this C will fail. They don't all commute. In fact, specifically what goes wrong is that if you calculate the commutator of J squared with J1Z, that's not 0. Okay, and also J squared, J2Z is not a 0 commutator. Okay, it is true that J squared with J1Z plus J2Z, that does equal 0. Okay, and that's why here we could have a CSCO that had both of those, but we can't have a CSCO that has this one and this one or this one. Okay, so the answer is no. Unfortunately, if we had the CSCO that included all of these things, then we wouldn't have to do any switching back and forth between bases. Everything would be nice, but that's just not the way things are in quantum mechanics. Okay, so that's the problem. Find these coefficients that we're going to try to solve. So before continuing, let me mention 2 classic examples of this. And the classic examples are so classic that we're actually going to do them first before trying to do the general version of the problem. For one thing, that'll teach us some lessons about how to approach the general version, and also it's easier. So one classic example is just when you have two spins of distinct particles. And we're going to ignore the orbital angular momentum. So in this case, J1 is just going to be S1. J2 is going to be the spin of the second particle. Okay, and so I just imagine there are two particles whose positions are nailed down so they can't go wandering off. One of them has a spin that's pointing in some direction. The other one's pointing in some other direction. Maybe there's a Hamiltonian that involves the dot product of those two spins or something like that. That's a very typical situation. But we're not too worried about what the Hamiltonian is. We're just trying to understand the space of states. And so we'd like to be able to understand how to add these two and get the product basis. The product basis is easy. We want the total spin basis. Okay, and so you define S, the total spin, to be the sum of the individual spins, and then you look at S squared and S sub z, and that's your complete set of computing observables. Okay, the second classical example is one we've already talked about, and that's J1 is L, and J2 is the spin, the orbital and spin angular momenta of a single particle. Okay, now these are examples that commonly occur, but some other examples that might occur, I'm not going to write this as a third possibility because we're not really going to get to it for a while, but you could consider, let's take the carbon atom. Okay, and for the carbon atom, there are 6 electrons. Okay, and so there's the total spin, which is S1 plus S2 plus S3 plus S4 plus S5 plus S6. And there's the same thing for orbital. Okay, and so one can do this by first combining those two spins, then adding in this spin, then adding in that spin, and you keep going, and then you do the same thing with the orbital. And so you have to do this many times in principle. And then once you're done with that, then you add together the orbital and the spin angular momenta that you got for the totals to get the real grand total J for the whole atom. Of course, that's not actually including the nucleus. That's a whole nother story that you could add that in as well. Okay, but this is actually complicated somewhat by the fact that these are identical electrons, another thing we will get to in the next semester. Okay, now typically when you're combining two angular momenta, you fixed the total angular momenta J1 and J2, and notice that appears in both orthobases. And so it's very common if you're going to write one orthobasis, for example, the product orthobasis. I'm going to write these in a different order this time. Okay, then I can just ignore the first two labels and write this as M1, M2. And the other basis has labels that look like this. M. And so again, because the first two labels are just common to both, I can suppress them and just write my states like this. And so then the problem again that we're trying to solve is we want to write Jm as a linear combination of M1, M2. Our problem is to find these coefficients. That's the general goal that we have. And it turns out, we'll see how this works. If you can find the coefficients, then you can do the reverse. So you can write M1, M2 as a linear combination of the total angular momentum basis kets. And it turns out the problem is very simple in the sense that if you know these coefficients, there's a very, very simple way to get these coefficients. So that's what we'll do. Okay, one last thing about notation is it's unfortunate that whether we're writing things in terms of 4 numbers or 2 numbers, there's a possibility that we'll get confused and I'll write down an M1, M2 state and you'll think maybe I'm writing down a JM state or vice versa. So one way to get around that is if we're using symbols like M1 and M2, then it's clear that we're in the product basis. And if I'm writing symbols like J and M, then it's clear that we're in the total angular momentum basis. But what if I'm writing down numbers rather than symbols? And the way we'll get around that is if there's any chance of confusion, then I'm going to write a colon between the M1 and M2 for the product basis. So if chance of confusion, separate numbers in product basis by a colon. So for example, I might write something like 1/2 colon 1/2, and then you would know that what I really mean is M equals 1/2 for the first one, and M2 equals 1/2 for the second one, and not J equals 1/2, M equals 1/2. All right, so next time we will start working through the examples. We will do the first classical example first, and then we'll get to this one. And those will be warm-ups to where we'll do the general case of adding together any 2 angular momenta. And then once we can do any 2 angular momenta, we can do something complicated like this case, at least in principle. All right, so that is it for today. Are there any questions about the lecture? All right, if not, let me stop the recording.